Hello, my name is Martin Robinson. I'm the CEO of Iris. We're manufacturers of electrical maintenance safety devices. This webinar is really going to discuss the growing skills gap that we're seeing in the industry today and how technology and the way we're working is evolving to deal with this skills gap. So when we look at the skills gap, one of the biggest areas obviously is, it's not so much the engineers and web designers and everything else that's where we're seeing a shortfall. The biggest shortfall we're seeing is electrical engineers, welders, etc., the more artisan trades. This is a growing void and it's something that is really concerning industry and the managers that have to deal with these problems on a day-to-day basis. Now, this is the results of an article from Forbes. And what we can see here, two primary here, electrical and electronic repairers. Now, if you look at that, we're talking about 72% of those workers are over the age of 45 and 35% are over the age of 55. Now, compare that again to electricians, where electricians, 64% are over the age of 45. Yeah, and nearly 25% are over the age of 55. So we have a huge void here. What we haven't done is backfill this skills gap, and by not backfilling that, the managers in the future are the ones that are really going to have the problem. So we are starting to now look, how are we going to deal with this void, between us catching up with training our engineers and maintaining and running our equipment and plant safely and efficiently. So why do we need effective electrical maintenance programs? Obviously, those have been involved in maintenance and reliability for a long time. We have very, very well established mechanical reliability and maintenance systems. And, if you look at electrical maintenance, it's all sort of been the red-headed stepchild of maintenance for some reason. But that's changed slightly in the last few years. And we're seeing a quantum shift now towards people looking at the reliability of their electrical systems. But this is the issue. The same old thinking and the same old results. What we're seeing now is, the way we used to do things, is not working. If you look at it, the equipment that we were working on 25 years ago is similar to the equipment we're working on now. However, there have been advances in the mechanics of the systems, but we're still utilizing the same maintenance. That doesn't work. So if you look at technology, especially in condition monitoring, that's advanced significantly over the last 25 years. So we've now got to start realizing, look, let's get on board and start utilizing condition monitoring to do our equipment maintenance. Now this slide shows 5 light bulbs, and really the question is which one of these isn't working. So obviously, as there are sort of long-winded ways of testing these, or we can do resistance tests, etc., etc. Just to verify that, but the most simple method of testing these is to switch them on. And once you can see as they're switched on, you can see bulb number 1 is functioning correctly. Bulb number 2 is complete system failure, zero light. Bulb number 3 is working, but it's much too bright, so it's still classed as a system failure. Bulb number 4 is functioning correctly. And if you look at bulb number 5, obviously it's working, but it's too dim, so it's still a systems failure. So electrical inspections must be inspected under load. I mean, if you look at standards like NFPA 70B, for instance, they say that you need a minimum of 40% load. Now, some of our systems are so well designed that we don't run at 40% load. There's so much redundancy, where other systems have been stretched so much they might be running 110% over their original design values. So there's lots we've got to look at. Now, what we tend to look at, if you look at in the condition monitors, we use infrared, ultrasound. So ultrasound, we're looking for 40 kilohertz emissions. Partial discharge. Now, partial discharge is typically over 4.5-5 kV. But we can do PD inspections. Motor current analysis, this can be done energized and de-energized. Ultraviolet is being used extensively now, especially in the power generation fields. Again, it's for identifying corona over 5 kV. And the most important thing is visual inspection. So this is what we do. If you look at the core fundamentals of condition monitoring, these are the tools and techniques that we will use to identify the condition of the actual systems or circuits that we're looking at. So where do we start? Failing modes effects analysis. Yeah. Now, with that failing modes, first and foremost, we want to identify the components that I want to inspect. So in electrical systems, they're typically cable connections, bus bar connections, and isolator or circuit breaker connections. These are really, I don't see, other than through human intervention, bus bars failing or cables failing outside of their joints or connections, and that's a broad spectrum thing. There are systems that do fail like that, but again, these are typically where we're looking at cable connections, bus bar connections, and the isolator and circuit breaker connections, the mechanical parts of the system. So what I have here is a good electrical connection. Yeah, traditional testing for this type of task, and we have to shut down. We can maybe do load bank testing, mega stress testing, tightness, torque checks, etc. There's a whole bunch of testing I can do on this circuit to show that it's correct. Yeah. Now all these maintenance tasks are designed to confirm whether or not the circuit connections are good and the systems meet its operational requirements. Okay, so this is why we do this shutdown and this testing, but it's antiquated. You can only tighten a bolt or a screw or a nut or a bolt so many times before it breaks. Yeah, and we've seen people where they've tightened the connection because they think it's a loose connection, but it's not. It's a lug or something that's causing the issue. So there's better ways that we can do this. Now, if we look at this circuit, now I'm going to do this through condition monitoring. So the infrared shows 0, ultrasound shows 0, PD shows 0, microcurrent analysis shows 0, ultraviolet shows 0, and there's no issues with the visual inspection. Here I've done all of these tests and there is nothing wrong with the connection. Now, that really to me means there's nothing physically that I can do from a maintenance intervention standpoint to make this connection any better. I've proven to you by looking at this connection that there's nothing wrong with it. So we just move on. Yeah, we move on. Now, if you look at an overloaded electrical connection, by utilizing the same test equipment, the infrared scan is going to show me uniform heating of the circuit. Ultrasound possibly is not going to show me a lot at this stage. PD, again, if it's over 5 kV, we might see them, but again, for overloads, this isn't really a circuit failure, this is a system failure. Yeah, so we're not going to see anything. Microcurrent analysis, possibly not, only from the load readings, obviously. Ultraviolet scan is not going to show me anything, and the visual inspection, only in super extreme cases where the heat damage has got so much on the cables, will we see the visual verification of that fault. So all of this we're looking at, and there's nothing wrong with it. So again, with this we're looking at, we can see an overloaded electrical connection, and we can do what's required to bring that back into the scope of works that's needed. Now, if you look at a high resistance or loose connection, yeah, here with the infrared, I'm going to see localized overheating. The ultrasound, again, I may find arcing, tracking, or corrosion. Corrosion obviously depends on the voltage, but on the medium to low voltage, we're going to find arcing or tracking in extreme cases. PD, possibly not only if it's 5 kV or above. Microcurrent analysis, yes, I'm going to find this. Ultraviolet scan, again, only if 5 kV or above. And the visual inspection, again, in extreme cases where it's got that hot, where it's actually visually discolored the system, the circuit, we can see the evidence of that. So again, now I can utilize these condition monitoring techniques to show me if I have a high resistance or loose connection. Now, another area where we have some similarities is obviously a loose cable lug. Now, that is going to give me identical results to a loose or a high resistance connection. Okay, but the actual high resistance is now in the lug and not in the bolted connection. So I'm going to get all the same results. So what we say here is typically as an electrical engineering firm that we would advise, if you find an overheated connection, that you would actually cut the lug off. You would replace the lug so the whole system is good and rebuild it. Now the reason we do that is if you're shutting down to do this, the last thing you want to do is go back in and change it. Say you need another shutdown because it wasn't the actual connection that was loose, it was the lug. So to save yourself embarrassment, just cut the lug off, replace the whole joint, and then you have a good system there in place. Now the final failure mode we're going to look at now is partial discharge or cable insulation failure. Typically partial discharge doesn't produce heat. Only in very, very extreme cases have I seen reports of heat being produced. But then we're getting into the arcing and tracking sort of side of life. So typically in infrared, no heat. However, ultrasound above 5 kV, we're going to hear corona. Partial discharge scanning using PD or UHF scanning, we're going to see that again. Don't forget, PD is typically 5 kV or above. Motor current analysis, we're probably not going to see much of motor current analysis. Ultraviolet scanning, yes, we will see something, again, over 5 kV. And then obviously the visual inspection is super important because the mechanical failures of partial discharge produces acids which produce residues, white residue, which a lot of electricians have seen. And this is very important to find. Okay, so very important to find, and it really underpins the importance of a visual inspection. So another thing that once we've identified the failure modes, we're going to start looking at failure patterns. Now, there's typical failure patterns. Okay, we have what we call age-related failures and non-age-related failures. So if you look at this typical failure pattern curves here, you're going to see that about 11% of failures are what we call age-related and 89% of failures are non-age-related. Now, these numbers can change significantly, but the ratios sort of tend to stay the same, where age-related failures are responsible for a lot less of the failures that we see than the non-age-related failures. So where that really tells me is if I'm using a calendar-based maintenance schedule, which is sort of a typical mindset and thinking, that I'm only going to find the age-related failures. That's what that sort of methodology is. That methodology of using calendar-based maintenance is typical to traditional thinking, which is the bathtub failure curves or the age-related failure curves. Therefore, that will deal with that. But what we've shown is really, if you look at most of the failures being non-age related, then you're going to be condition-based to find these non-age related failures. So this is the quantum shift. Start thinking that way. Start thinking about, reliability and maintenance as being two different things. And what we're trying to do now is use condition monitoring to assess the reliability of the system. Yeah, and that really is starting to look at finding these non-age related failures, which are the cause of the majority of the failures that we're going to see in our systems over its life cycle. Now I'm going to introduce you to something now called a DIPF curve. Now DIPF, most people call the PF curve, but the DIPF curve is really where we've extrapolated that out for the whole life cycle of the system. So where the DIPF is, D is design. Yeah, so with design, people are now starting to look at, from an asset management standpoint, if we design it correctly, we're going to have it done right. So a big part of design is getting the OEM involved right up front. Yeah. So the OEM is going to be there to really assist you on designing and the reliability for your project. Yeah. And then these directly impact the following statistics. Yeah. As much as 60% of failures and safety issues can be prevented by making changes in design. 80% or more of the facility's lifecycle cost is fixed during the plan, design and build phases. So again, getting it right up front is really going to pay back over the total cost of ownership or the life cycle of the asset. And finally, 30 to 40% of the equipment breakdowns are related to poor equipment design or condition. So again, getting right up front in the design point of the life cycle curve is really going to give long-term paybacks. Now, a term I hear used a lot is designing for reliability, so system design or design for reliability. Now, primarily there are three principles, in system design for high availability engineering. Number one is we try and eliminate single points of failure. Providing redundancy to systems. So failures of components doesn't mean complete or entire system failure. Secondly, we need reliable crossover points. Yeah, and unfortunately, sometimes a crossover point tends to become a single point of failure. So high availability engineering provides reliable crossover. And then finally, we really need to detect the detection of the failures as they occur is super important. Yeah, so if the two principles above are observed, you may never see a failure, but your maintenance and reliability activities must be designed to detect early signs of failure. Now the I part of it obviously is the installation. So we have installation. So design and installation is a big thing on there. And here we start to see, if we look at the DIPF curve, P is point of potential failure, F is a functional failure, and after functional failure we have total failure. So what we're trying to do now is, if you look at in between installation and point of potential failure, is what we call a proactive domain. That's where we're starting to do all this condition monitoring. Now when we find the problem, point of potential failure, that means a changing thing, then we're starting to work in the predictive domain, and then we go into what we call our fault domain. So if we break into this a little bit more, we can see here that from the point of potential failure, we're going to look at these early signals, and I'm looking for to utilize CAST, critical asset surveillance technologies, to detect problems early. So if we can find these problems early, we can repair them early. And obviously, if you look at the graph here, the bottom line, the cost of repair, the longer you leave it, the more expensive it comes to repair. Now, breaking into the PF curve, let's have a look at early signal 1. Now, at this stage, we're going to use the primary tools in electrical inspections: ultrasound, partial discharge testing, infrared, motor current analysis or voltage and current measurement, and the visual inspection. So, looking at this, we're using that equipment, looking at the results. What we would see at this stage is possibly we may detect corona, which sounds like this. And remember, corona is voltage dependent. Your motor current analysis may start to show slight increases in the resistance measurements at this stage. There should be no abnormal thermal patterns detected, right? But all the time we're doing this utilizing EMSDs, electrical maintenance safety devices, such as IR windows, ultrasound ports, voltage tap-off ports. The panel stays closed and guarded all the time. It's a very quick and easy inspection done under full load condition. Now, if we allow this to go further, we'll get to what we class as early signal 2. Now, again, we're utilizing the same equipment, but the results will start to escalate. Now, at this stage, we're going to sort of now possibly pick up tracking. Now, tracking is, unlike partial discharge testing, is not voltage related, or corona, sorry, it's not voltage related. So we'll find tracking in low, medium and high voltages, and really this underpins the benefits of using ultrasound testing and partial discharge testing when we're looking at electrical equipment. Now, tracking sounds like this. So quite distinctive and very easy to pick out. Also, at this stage, motor current analysis, or the voltage and current testing, is going to start to show the early signs of failure, and we're going to start to see thermal patterns develop around the failure points. So there we have a visual verification and audible verification of this fault developing, and all the time we're using EMSDs and the panels in a safe, closed and guarded condition, and it's very quick and easy to do. So the final stage of failure, or early signal stage 3, we're going to utilize all the CAST equipment that we've just discussed, but again, things are escalating all the time. Now, when we start to pick up early signal 1 or early signal 2, we may increase our inspection frequencies, because obviously we know that we're on that failure curve, and we're trying to, get this through to a time where we can repair it when it's suitable to repair with our operational requirements. So at this stage, we'll probably pick up something called arcing. Now, this is the final stage of electrical failure, and if you hear arcing, that's critical. I mean, you would shut down immediately. You wouldn't even open this panel at all. It's just far too dangerous. And arcing sounds like this. So a very, very distinctive sound. Obviously, again, at this stage, the motor current analysis and the voltage and current testing are going to be showing significant signs of failures. Your thermal patterns are going to be critical. So again, all this is done through your EMSDs. Totally safe, quick, efficient, and the panel remains enclosed and guarded in a safe condition. Okay, so very, very simple process to do to make these measurements. So if you enable it to just go on in the PF curve, now you're going to start to come into the other issues. If things get hot to touch, the audible noise, so mechanical and audible failure are going to be very evident. And again, if you look at it, the cost of repair. The longer you leave it, the worse it gets, the more expensive it gets to repair, to such an extent where it just isn't feasible to carry out the repair, and you're doing a complete asset swap. Now, when you look at the value, the true value of condition monitoring, if you like, or CAST, is that we can extend the life cycle by, finding these points of potential failure early, repairing them early, so no significant damage is caused to the system, and that way we can just build it out and it works fine. So the final part, electrical maintenance now is very heavily risk orientated. And one of the things we have to calculate when we're looking at failure modes effects analysis processes is something called an RPN, or a risk priority number. Now this risk priority number, typically, there are different ways of calculating this, but this is the most used. We typically use 3 areas. We look at the severity, i.e. the severity of failure from 1 to 10 on anything affecting life or limb would always be a 10. But the severity is based on business risk, human risk, financial risk, whichever drives your facility. Second thing is probability number. So how likely is that fault to occur? From either historical analysis or mean time between failure data. There's lots of things that we can get for the probability number. And the final thing is the detection number. How easy is it to detect these faults? Okay, so each one of those carries a score from 1 to 10, which basically gives us an RPN of anywhere between 1 to 1,000. Okay. And once we calculate those RPNs, what we would do is plot them on something called a heat map, or a risk matrix. There's lots of different names for this. But by calculating those and placing them on this heat map, then we start to look at, something which many clients call the risk appetite. So what risk appetite really is basically, you need to understand the risk to the business of the failure of your critical assets. And you take the results of that risk assessment and you would utilize that in your heat map when looking at your maintenance and reliability requirements. And you would plot, where your things are. So typically what we're showing you on this graph here, for instance, is, the first part, you might say we're only going to do that annually because there's no risk to the business. Then you might say semi-annual inspection, quarterly inspection, monthly inspection, or even go to 24/7 online monitoring and much more advanced systems. All of these will be driven by the risk priority number and your risk appetite. Now, be very much aware, if you have a low risk appetite, you will have a high maintenance or reliability bill. If you have a high risk appetite, you will have a low maintenance or reliability bill. Okay, they are adversely affected by one another. So where are we? So we know we have an issue with skilled labour, and that is only getting worse, and we're now looking at strategies to sort of what we call bridge this skills gap. So how do we start going around bridging this skills gap? Well, one thing that we recommend is CAST, Critical Asset Surveillance Technologies. So what CAST is, it starts to look at risk, etc. Now, this graph here shows a study that was done by IEEE. And what it basically showed was it basically compared strategies without a planned maintenance or CAST program against those with a planned maintenance or CAST program. And what this study basically showed was there was a 66% less reduction in risk when utilizing a planned maintenance or CAST system. Reliability, so reliability engineering would show a reduction of 66% of risk, which really is pretty evident, because what you're saying is like, okay, we're going to look at this stuff more routinely. So if something's going to fail, we're going to find it early, i.e. using the DIPF curve, and really it speaks for itself. So the results of this study is no surprise when you look at the strategy you're going to be utilizing of reliability and condition monitoring versus maintenance, calendar-based hands-on maintenance. So if you look at what does CAST mean? So basically CAST is a 100% surveillance repair model, and basically what I mean by that is we only repair the faults that we find through routine surveillance of our assets. Now, what that does, it really impacts the risk priority number, because basically the detection multiplier is decreased to a 1 because the actual EMSD, electrical magnetic safety devices, provide access for the inspection. So there are no issues with actually detection of the fault, and basically through detection the likelihood of failure is reduced significantly. So by utilizing CAST and EMSD strategies, we're going to impact the likelihood of failure and the detection of failure to very, very low numbers. So even if you're on a 10 on the issues caused by the failure, yeah, by having the other two multipliers much lower, the RPN numbers are going to be low. Yeah, so that's what we're trying to aim for here. So what the surveillance methods that we utilize in a CAST program are like infrared thermography, airborne ultrasound, motor current analysis, PD testing. Power quality management is something you might do. Ultraviolet cameras, again, is something you might do. Vibration analysis, especially on rotating motors, etc. The electrical faults will give a different vibration signature, and we can detect whether it's mechanical or electrical in motors, pumps, etc. Alignment testing, visual inspections. You can start to add oil analysis. All of these things can be brought into a CAST program depending on what you're doing. So it's limited. So it's not just limited to the things I'm showing you on the screen here. So training is imperative, especially as we know we have a skills gap issue. So the CAST training program has been broken down into a number of levels. The first level basically is what we call the ICAST, Introduction to CAST, but we're trying to introduce the concepts of reliability and condition-based maintenance techniques. This is what we're trying to do, and the CAST training program is a journey. It basically takes you from the understandings of the basics of reliability engineering and how we implement condition monitoring and how we implement EMSDs and we start to grow that strategy all the way through to what we class as a CAST master technician. Now, as stated, the first step, if you like, on the CAST technician training path is what we call the entry-level CAST technician. Now, this is a 3-day training course, no prior experience required, and really it's just designed to take a guy on his first steps into reliability. They're primarily aimed at probably young apprentices or entry-level guys coming into engineering. But again, don't forget, this is purely data collection. There's no diagnosis involved in this. There are people much more experienced in the organization would be involved in diagnosis, but this is purely data collection. So let's have a quick look at the 3-day training course for the ICAST. So basically, we would go over environmental health and safety, very important. Safety first, always. Introduction to reliability maintenance. So why are we doing this? What are the failure patterns, failure modes, PF curves? I've always believed that the best plans from implementation start from full disclosure, so everybody knows why we're trying to do this. Then we're going to look at the introduction to CAST technology, so infrared, acoustics, ultrasound, partial discharge, power quality. We're going to give them a high-level overview of these technologies and how they interweave in an holistic maintenance model. But we're going to be very heavy on the infrared and acoustics and the partial discharge at this stage, because that's what we're going to utilize as the primary tools within the CAST inspection program. We're going to look at why implementing a CAST maintenance program, how you select route data, route selection and data management, something we're going to review here as well. And we're also going to go over EMSD, so the inspection systems and a high level view of IoT, Internet of Things solutions. Now, the student will need to pass a written examination and proficiency tests in the use of CAST technologies and pass practical tests relating to the measurement and data recording through EMSDs. And again, remember, this is data recording only. This is not fault detection and management. Now, the next level, if you like, in CAST technician training is a level 1 infrared or ultrasound. Now, this stage, the technician will choose which training route they want to take. They can choose to either go on the infrared training route or the what we call airborne emission, which is ultrasound and partial discharge route. This is a 4-day training course. Builds on the 3 days they've already done. They must have completed the ICAST and must have had at least 210 hours experience working as a technician in CAST programs, and these hours must be logged. So again, we're meeting the requirements of ASNT for the level 1 training. But again, we're just building again on this in much greater depth on this. Now we're going to start to get into fault detection and management. So at this stage, I would expect a level 1 technician to be able to at least tell me what the issue is with what they're looking at, etc. And typically this will build on their prior experiences as engineers working in programs. Now the next level is CAST level 2. Yeah, so it's level 2 technician. So this will be a level 2 training course in either infrared or airborne emissions, a 4-day training course, and must have completed level 1 in infrared or ultrasound. Now, this stage you're on the training path. So if you've gone on the infrared training path, you would now do a level 1 infrared, then do your level 2 infrared. You can't do a level 1 infrared and a level 2 ultrasound. You must have completed the level 1 course in that discipline and completed a further 420 hours experience in CAST programs as a CAST technician. Okay, so a CAST level 1 technician. The final stage in the CAST technician training path is what we call the CAST master technician. Now this is a very in-depth training course. It's another 5 days. You must have completed both level 2 in infrared and ultrasound. Okay, so you have to have completed both disciplines and 630 hours experience in each discipline as a level 2 technician. So again, there's a big background requirement before you can even go on this training course. And during these 5 days, we then start to build on the advanced infrared and ultrasound and partial discharge techniques. We go into the software management of sound waveform analysis and the ultrasound PD analysis, ultrasound program analysis. We also then start to build into some of more in-depth stuff on the other technologies. And then this guy really becomes your go-to guy within your organization. They're also qualified to do train the trainer to the lower levels, take the ICAST training on and some of the level 1 training for your entry-level guys coming in. So this really starts to really bring in, the reliability management piece into your organization. So, reducing maintenance-induced failures, okay? There is nobody on this planet that has never made a mistake. In fact, sometimes we learn more from our mistakes than we do our successes. So again, to err is human and never a true word has been sent. So maintenance-induced failures are real problems in the field, and we're trying to find ways to reduce those. Now, if you look at the latest version of NFPA 70 2018, 70 years actually has a complete section on human error, risk assessment due to human error. That's 110.1H. And basically it shows that we address the potential for human error. We look at the negative consequences of people, processes and work environment and equipment caused by human error. And there's an informative Annex Q, which basically is human performance and workplace electrical safety. So we're really trying to drill into this from a risk basis, and there's studies out there that say, 95% of issues are caused by human error. Again, you can take that as you find it, but again, we must admit, even it may not be 95%, but human error, and maintenance-induced failures are a big problem. And if we can get rid of those, it's a real positive step forward. So hence, this is where electrical maintenance safety devices start to come into their own. There are sort of different types of maintenance, electrical maintenance safety devices. Obviously, we have maintenance inspection windows. They can be round or rectangular. They are infrared transmissive, visual, infrared, UV, can be custom designed, etc. So maintenance inspection windows is one area we go to. The second is ports, so ultrasound or partial discharge ports, external voltage indicators, motor current analysis tap-off points, power quality analysis tap-off points. All the time we're trying to bring out these data collection points to the front, and the safe side of the electrical panels that we're working on. And then finally, we're really advancing into the online monitoring, temperature monitoring, asset tags, data management, vibration analysis, PD analysis, power quality analysis. This is really starting to grow with the industrial Internet of Things and the adoption of that within industry. People are starting to utilize the vast amounts of money their organizations have spent in online systems, and basically piggybacking the reliability data is a great way forward. So if you look at maintenance inspection systems, you're looking at this image, you can see here that the guy is looking in there doing a visual inspection, having completed an infrared, taking his ultrasound data through an embedded port. Yeah, in here we also show a Delta T alert system, which is online temperature monitoring, and we show an eSentry Connect system, which is basically the data management piece of this. And all of this becomes a maintenance inspection system, basically a data collection point for the health of the asset that you're looking after. So eSentry Connect, as I say, that's our system. It controls, it manages the data. It can be site-based or standalone or cloud-based subscription. Very useful system, manages the data of the inspection locally at the point of inspection. I have a record of the prior inspection and I can do route management. There's all sorts of things we can do with eSentry Connect, and you can visit the website and find out a lot more about that. But again, this is about growing your inspection system. Now, obviously, Delta T Alert is an online monitoring system, either for temperature, humidity, power, current measurement, thermocouples. There's a whole bunch of things you can build into this, and these are IoT-based solutions that go within the mechanical systems of the actual maintenance inspection windows. So, as I stated earlier, 70E is a real risk-based standard now, and by working with EMSDs and CAST programs, we're working in the finer points of the hierarchy control, fundamentally through elimination and substitution. Okay, so this is where we're trying to move CAST and EMSD programs to. We're trying to make it safer for the people using it because we maintain enclosed and guarded systems, and we're also trying to maintain the data that comes from these inspections and minimize the skill sets required for the data analysis piece. Yet we then have allocated our primary skilled engineers and electricians, mechanics, etc., who go in and fix things. They're not involved in data management unless they're needed to be. Yeah, they're involved in fixing the problems and keeping things running. Now, there was a study done by Emerson that showed what the effects of regular skill preventative maintenance combined with remote monitoring of critical power systems reliability. And basically we were looking at the effect on mean time between failure. How does this work? Now, what their study showed that basically, if I was to look at putting online monitoring on a system and let's say do quarterly inspections through an EMSD, which makes it really simple to do, we turn hours into minutes basically, that by doing a quarterly inspection, we can increase mean time between failure by up to 51 times. If I wanted to do a bi-monthly inspection, I can increase MTBF by 82 times the original MTBF. So these are very, very significant figures. And if you're involved in power management and you can't afford a shutdown, then utilizing these systems is really going to be a big payback to your organization. Now, when we look at asset management, we have a thing called total cost of ownership. And one thing that surprised me when we looked at total cost of ownership was where these allocations of costs were. Now, direct costs such as acquisition, research, design, and production, test, and construction, I historically always thought that was where most of the money went, but actually it wasn't. I mean, it's in the indirect costs or invisible costs. Yeah. So, for instance, the operations and maintenance budgets, testing and support, spares, inventory, training, software disposal, who are actually responsible for the lion's share of the total cost of ownership. Yeah, and in some instances, these numbers were vastly different to what I thought. Yeah. Now these can change significantly depending on the industry, but that one thing is for sure is the indirect or invisible costs are always significantly more than what we see up front. Now, if we break that down, by getting involved in CAST and EMSDs to utilize very simple data collection, yeah, we're going to have an impact on some of the primary areas, so i.e. operations, maintenance, testing and support, spares and inventory, because again, we're going to be working on condition-based data to run through this. So that is probably responsible for about 75% of the invisible costs or indirect costs. So if we can have an impact on that, the lion's share of our indirect costs, then we're going to have a real impact on our total cost of ownership. Okay, how much it depends on what we do and how we do it. But one thing is for sure, that condition monitoring of electrical systems utilizing CAST and EMSDs will significantly impact the indirect costs of a total cost of ownership. and is one thing to be considered very carefully. So in summary, the use of EMSD CAST programs deliver the following. Yeah, we simplify the inspection programs, bridging the skills gap by utilizing what facilities we class as a rounds and readings inspection scenario. We send people trained to ICAST, the entry-level data collection, to go around and gather the data and upload this data so people can review it. Yeah, and we can trend the data and start to forecast any issues that might be coming up. Our risk exposure is 66% less by utilizing a CAST plan maintenance program. There's significant impact on what we call TCO. I just said we reduce the indirect costs associated by up to 75% of TCO, so we can have a real impact on that. Yeah, the risk priority number is significantly reduced by obviously increased fault detection. Mean time between failures significantly improved by adding to the increased uptime and decreased downtime. Maintenance-induced failures removed by simplifying energized maintenance inspection processes. If you can't get into it and you can't touch it, then the likelihood of you having an accident is relatively low. Yeah, I can't really make it any lower. Okay, so we're utilizing data-driven maintenance, if you want to look at it that way, but the CAST and EMSD program ensures that I can get all this data with never putting anyone in harm's way. And finally, we can increase the return of investment on our CAST equipment and training. So the training that we're going to put in and the equipment we're going to buy is going to be used extensively. It's not going to sit in a cupboard waiting for someone to pick it up because they think it's a problem. This will be used extensively. Okay, that's the whole idea of doing this. So this is one of my favorite quotes by the great Edward Deming. Without data, you're just another person with an opinion. We need the data from these machines so we can make a good judgment call on the maintenance that's required, if required. Yeah, and if it's not required, we can show why it's not required, because you can't, if it, as I said before, if it ain't broke, don't fix it. When it comes to systems, that works, or should we say components and etc. But when it comes to the strategies we're using, we've got to move forward. We have to change our way of thinking. How can we be doing the same type of maintenance that we were doing 30 years ago? It doesn't make sense. Equipment's changed. The actual monitoring equipment that we have, the evolution of IoT, all of this is in place. So we have to jump off of that mindset into a mindset that embraces condition monitoring. Yeah, if we embrace condition monitoring, we will get a lot more from our systems, a lot more from our people. They're going to be safer, yeah, and we're going to reduce the likelihood of failure, and it's just a win-win-win across the board. I've finished rattling on the webinar. At this stage, we're open for questions, so let's take questions from the audience. Thank you.